modulation has three basic techniques. First, amplitude modulation. Second, frequency modulation. And third, phase modulation. The peak frequency deviation and modulation index for frequency modulation modulator with a deviation sensitivity that's given and a modulating signal. So, we must find the peak frequency deviation. For frequency deviation, we use the formula K1 equal to K1 multiplied by Vm. K1 is deviation sensitivity and Vm is given here. Okay, so K1 is 5 and Vm is 2. So we got 10 kilohertz. Then we find the modulation index. Modulation index, we use formula frequency deviation divided by Fm. Frequency deviation, we got 10 kilohertz. So Fm, we got from here 2 kilo. We divide and we got 5.
Bessel function. The equation that expresses the phase angle in terms of the sine wave modulating signal is solved with a complex mathematical process known as Bessel function. Bessel coefficients are widely available and it is not necessary to memorize or calculate them. So this is how the Bessel function is being calculated, and this is the answer from those complex equations.
This is example for the Bessel function. For n Fm modulator with a modulation index m equal to 1, a modulating signal Vm equal to Vm sin 2 pi 1000 t, and an unmodulated carrier Vc equal to 10 sin 2 pi 500 kt. Determine the number of set of significant side frequency and their amplitude. Then draw the frequency spectrum showing their relative amplitude. So from the Bessel table, m equal to 1, so the J0 is 0.77, J1 equal to 0.44, J2 equal to 0.11, and J3 equal to 0.02. So n is equal to 3. To find the amplitude, so Vc from the equation is Vc equal to 10. So V0 equal to J0 times with Vc, which is 0.77 times 10 equal to 7.7 volt. So V1 equal to 4.4 volt, V2 equal to 1.1 volt, and V3 equal to 0.2 volt. Okay, this is how to draw the frequency spectrum. So Fc equal to 500k, Fc minus Fm equal to 599k, Fc minus 2Fm equal to 498k, and Fc minus 3Fm equal to 597k. So Fc plus Fm equal to 501k, Fc plus 2Fm equal to 502k, Fc plus 3Fm equal to 503k. 7.7 is a V0, 4.4V is a V1, 1.1V is V2, and 0.2V is V3.
Continuation from the Bessel function is the Fm bandwidth. Theoretically, the generation and transmission of Fm requires infinite bandwidth. Practically, FM systems have finite bandwidth and they perform well. So in FM bandwidth, there are two kinds of bandwidth. So first one is bandwidth for FM is equals to 2 times number of sideband pairs times with modulating frequency. Second one is Carson rule, that is also kind of bandwidth, and the formula is 2 times deviation frequency plus modulating frequency.
For An FM modulator with peak frequency deviation data f equals to 10 kHz and modulating signal frequency FM equals to 10 kHz, VC equals to 10 and 500 kHz of carrier. Determine 1. Actual minimum bandwidth from Bessel function table. So to find actual minimum bandwidth, we will use this equation, be the bandwidth equal to 2 and FM. To get n, we find it from the table. Before we get it, we must find modulation index. Modulation index equals to deviation frequency divided by FM. So 10 kHz divided by 10 kHz equals to 1. And from the Bessel function table, we get n equals to 3. So 2 times 3 and FM is given here, 10 kHz equals to 10 kHz. So 2 times 3 times 10 kHz equals to 60 kHz. Second question, approximate minimum bandwidth using Carlson rule. So Carlson's rule is different from the minimum bandwidth. So it use new formula, that is 2 times deviation, frequency deviation plus width FM. So 2 times 10 kHz plus 10 kHz equals to 40 kHz. For the third question, plot the output frequency spectrum from Bessel approximation. So from the Bessel approximation, we get the value m, and we can find it from the table. So the value here is from the table, and here is the FC frequency. So here is FC plus FM, and this side is FC minus FM. That's all.
This is the example for the indirect method. We choose Armstrong indirect frequency modulation. So this is integrator, narrowband phase modulator, crystal control oscillator, frequency multiplier, mixer, LPF frequency multiplier. So this is section A, section B, section C. N1 equal to 162, frequency 1 84 MHz, N2 equal to 30. So NPBM output, we have frequency equal to 500 kHz and frequency deviation 15.432 Hz. We need to find the frequency and frequency deviation at section A, B, and C. So we start with at A. Frequency will start with 500 kHz times by 162. So it will equal to 81 MHz. Frequency deviation, we take this 50.432 Hz times by 162 equal to 2499.984 Hz. For at section B, frequency 84 we take from the mixer. We know that frequency 1 equal to 84 MHz, so it minus by 81 MHz from the F frequency at A. So we have 3 MHz. For frequency deviation, it's same with the frequency deviation at A. So at C, we can see that frequency equal to 3 MHz. We take from frequency B. B is 3 MHz, it times by 30. So it will equal to 90 MHz. And frequency deviation, we take from at B 2499.984 times by 30, and it will equal to 74.99952 kHz.
Noise in FM. In AM system, noise easily distorts the transmitted signal. However, in FM system, any added noise must create a frequency deviation in order to be perceptible.